So the next speaker is Hao Ni from UCL, and the title is Learning to Approximate Controlled System. Please.
I don't have the paper to make So thank you very much for the introduction, and it's my pleasure to give the presentation here. Today I'm going to talk about how to design an efficient algorithm to learn the unknown control differential equation based on the rough path theory. So let me start with the motivation of our work. So I'm interested in predicting the influx of the data stream. So what is the data stream? Data stream refers to the data sets which continuously grow over time, and it has become ubiquitous nowadays, and it's one of the main data type to analyze. For example, high-frequency financial data is one of the data stream, and very often people are more interested in extracting useful information out of the data stream to make the better decision. Let me give you an example in finance. So the future market movement can be thought as the influx of the historical market information, and the investor would like to understand it to make better trading strategy. So on the abstract level, all those applications can be formulated as the supervised learning problems on the path space. So here we consider the input x represents a data string, which is a continuous function with respect to time. We call it a path, and y represents the influx of the data string. So the interaction between x and y is formulated in the standard way. That is, y is given by certain fixed but unknown mean function f acting on x and perturbed by certain noise. So the question we ask ourselves is, how can we estimate the unknown mean function f from the samples of the input output pairs x and y? This is a standard regression or classification problem. Depending on the type of the output is categorical or not. However, the main difficulty comes from the type of the input. Now the input is a path which lives in an infinite dimensional space. The main goal of our research is to design an accurate, efficient, and robust algorithm to learn the mean function f from the data to tackle the supervised learning problems on the path space. And in this talk, I will focus on the case of learning the unknown control differential equation. So here the output y is the solution to certain control differential equation driven by the input path x. So it provides a rich class of the functional on the path space, and also the control differential equations offers a general model to describe the complex interaction between the input path and the output. Eaton calculus actually can make sense of the such equation, while the driving path is a Brownian motion, and it's well known that it plays a foundational role in the derivative of pricing in the modern financial mathematics. There has been a rich study about the stochastic inference for the parameter estimation for the stochastic process. So our work is related to that. However, the focus is a bit different. In our work, we more focus on to predict the pathwise solution to the control differential equation without making any assumption on the parametric form of the vector fields. So the question here is, how can we learn the solution map IF from the many samples of the driving path x and the corresponding solution y at the terminal time t. So let me quickly recap what we can learn from the classical regression theory. So it's the same setting as before, but here the xi lives in the finite dimensional space. So although the mean function f may not be linear, if we can find the good feature set which can simplify the functional relationship between the features and the output, then in the way it reduces the nonlinear regression problem into the linear one, and we can solve these problems. So the lessons we learned from that have two folds. First of all, the choice of the features are quite important, and secondly, we can propose the nonlinear parametric forms for the mean function, for example, the neural network. And actually, any model with a universality can be used to calibrate to the data up to any given error tolerance level. However, using over-sophisticated model may lead to the overfitting issue. So overfitting is a phenomena of misinterpreting the noise as the actual signal. It usually happens when we use the very complicated model for our mean function, or use a very high-dimensional feature sets. So here, when we design the algorithm to learn from the data, we need to take into account the dimensionality of the data as well as the complexity of the model we used. So let's go back to our problem, the regression on the path space. So the naive way is, although the input x is an infinite dimensional object, but we can evaluate the x at the finite dimension, at a finite collection of the time points, say xt1, xt2, and xtn. And I called it the increment features. And Terry has already explained that such time series representation of the data may not be very efficient. And also, if you have a closer look at of this object, the dimensionality of this increment feature is proportional to the number of the sampling points. So that means if you have very high frequency data, you might have the overfitting problem caused by using such a feature set. So the proposed solution is to use the signature of the path as the faithful, efficient representation of our sequential data. So here I just to emphasize that the dimension of the truncated signature is independent with the frequency of the time series, which can avoid the overfitting issues caused by the high frequency sampling totally. So now let me give you a brief definition of the signature of a path. So it's a sequence of the iterated integrals. And I will make this part very short because Terry has already explained the main properties of this feature set. And here, intuitively, you can think the signature of the path is non-commutative for polynomials on the path space, and it serves as the basis function to span the space of the continuous function on the unparameterized path. So let me quickly recap the main idea. We start with to approximate the functional on the path by the uniqueness of the signature. It can be written as another function on the signatures. Because the signature is a basis function, we can find the linear functional on the signature. By the uniform estimates of the signature, hopefully the linear functional on the truncated signature has already captured the most information of the path. And the log signature of the path is an important concept related to the signature. Here, I just want to emphasize that if we truncate the log signature and the signature up to the same degree, they contain the same information. However, the dimension of the log signature is smaller. So the signature provides the unified way to analyze the time series of variable lengths on equal sampling on equal sampling. So the main idea is actually we lift the discrete or continuous time series into the same space. So now we are ready to propose our first signature model. So here we assume that the output y is given by the linear functional on the signature and perturbed by certain noise. The calibration strategy is pretty straightforward. We apply the linear regression on the output y against the truncated signature. And it has the advantage for the dimension reduction, and our method is non-parametric. Let me give you a concrete example of the learning the solution to the unknown stochastic differential equation. So in this case, yt is the solution to the SDE driven by the path xt, while the first coordinate of xt is the time, and the second coordinate is the Brownian motion. And here the integral is understood in the Stranovich sense. And so we simulate the 1,600 independent samples of the input path x and the corresponding solution y capital T. And here we choose capital T equals to 0.25. And we use half of the samples for the training and the rest of the testing. In order to benchmark our method, we will use the increment features. We apply the linear regression on both the increment features as well as the truncated signature. That's the result we got. So I plotted the model estimated output against the actual output. So when the points are closer to the line y equals to x, it means the prediction performance is better. On the left-hand side panel, this is the result for the increment features, and on the right panel, this is the result for the signature features. And here clearly you can see that even using the lasso and cross-validation, the signature feature outperforms the increment feature. It's noted that the dimension of this truncated signature is only 31. However, the increment features here is 750 because I use the number of the discretization step is chosen to be 750. This is the evidence to show that the truncated signature of the relatively low degree has already captured the essential information of the path. However, if we increase capital T equals to 1 and we redo all the experiments, this linear model on the signature produce a worse result as before. So we need to think about the better algorithm. So the underlying reason for this result is the linear model on the signature can be thought as the polynomial regression, which is only locally effective. So when capital T is large, we need a very high degree of the signature. However, it may lead to the overfitting issues. So the possible solution is, first of all, we can find the more effective features. For example, we can consider the log signature and so on. Secondly, we can combine the nonlinear regression methods in our framework. So let's go back to the control differential equation, and I will show you how to use the numerical approximation theory to help us design the more efficient algorithm to treat this case. So the idea is locally we can use the Taylor expansion to approximate the increment of the solution yt minus ys. So this is a linear combination of those iterated integrals of x. And this theorem gives the error estimates of such a Taylor expansion. So when the vector field is smooth enough, and here we can see that this error estimate has the order t minus s power gamma over p. So when gamma is greater than p, the exponent is strictly greater than 1, which allows us to place the local approximation to globally. So more specific, so if we have the time partition, that is a collection ui from time 0 to capital T, we can define the estimator of the y recursively. So y hat u0 is given by y0, and the y hat ui plus 1 is given by the Taylor expansion I showed you before with the starting point y hat ui. So here the y hat ui plus 1 is a function of the y hat at the previous time. Also, it depends on the signature of the path x from time ui to ui plus 1. Because we know there is a one-to-one correspondence between the signature and the log signature, so y hat ui plus 1 can be thought as a function on the log signature of the driving path x from time ui to ui plus 1, and also the estimator y hat at the previous time step ui. So if we define the estimator y hat in such way, we can prove that if certain regularity condition is satisfied, for any given error tolerance level, such estimator U capital N can approximate the actual solution Y capital T up to the error tolerance level. And here it's noted that we can see certain recursive structure of the error estimator Y hat UI. It reminds us of the structure of the recurrent neural network. So the recurrent neural network is composed with three kinds of the neurons. XT represents the input neuron at time t, and ST is denoted the hidden neuron at step t. And ST is given by the activation function f act on the linear combination of the previous hidden neuron st minus 1 and the current time xt. And the OT is denoted as the output neuron at step t that is given by another activation function act on the linear functional on the hidden neuron SL. So if we recall the estimator of the numerical solution y hat ui, you will see the similar pattern. Actually, you can intuitively think y hat ui as the hidden neurons of the I and N with the input that is the log signature of the x from time ui to ui plus 1. So that motivates us to propose the following model. So we have the raw data xti, which potentially can arrive at a very high frequency. Then we have another coarser time partition D, that is a collection of the time points ui. And from time ui to ui plus 1, we compute the log signature of the driving path x over this subtime interval. Then we will use the recurrent neural network using the sequence of the log signature as the input. So this is our model. So I'd like to end some remarks on the model we proposed. So when the coarser time partition D coincides with the original time partition and the degree of the log signature is said to be 1, our model is the same as the INN with the raw data. And our model has in addition, our model has the universality. That means when for any given error tolerance at level, and if we make the time partition is small enough and the degree of the log signature is high enough, we can approximate the solution using our model up to the error tolerance level. So here, the main advantage of our method is that it's more efficient in terms of the computational time because it reduces the time dimension of the INN significantly by using more efficient representations of the spatial features. So the proposed algorithm is we compute for the given time partition D, we computed the corresponding the sequence of the log signature of the drying path, and for any given error tolerance level, and we fixed the maximum number of the epochs, because here for the optimization part of we will use a gradient descent or stochastic gradient descent. So we learn the model weights until the error is smaller than error tolerance level, or it reaches the maximum number of the iterations. And we will compute certain metric to measure the goodness of the fitting, the R-squared or the mean squared error, and so on. So let's revisit the previous SDE I showed you before for capital T equals to 1. And this is the result we get. We vary the error tolerance level, and we compare our method with the INN with the raw input data. And here we can see that in the out-of-sample data set, both methods produce the comparable accuracy. However, our method is magnitude better in terms of the computational time. So we also apply this method to other SDE. For example, the vector, the drifter term include a certain periodic function. And here we consider the drawing path is due time and the Brownian motion. So we vary the degree of the degree of the log signature and the number of the time partitions over the whole time interval. That's the result we get. So there is a trade-off between the degree of the log signature and also the number of the segments. So because if we, for example, if we make the degree of the log signature is too low, we may have the underfit problem. However, if we increase the degree of the log signature too high, we might have the problems of the overfitting because it increases the dimensionality of the features. To benchmark our method, we choose the linear regression model on the signature and the INN with the raw data or folded raw data. So the reason we use folded raw data is because if you throw your data into the INN, it actually can't converge in days. So the folded raw data is we have the cost time interval. For each subtime interval, we use a time series representation of the path as the spatial features. So here you can see that our model produces much better results. So our method produces the best mean squared error among 3 methods, and it's more efficient compared with the INN with the folded raw data. But of course, our method is slower than the linear models on the signature because it uses the linear regression. So there isn't much learning time. But our method, however, the linear model on the signature may have the underfit problem. And we also try to vary the frequency, the sampling frequency of the raw data, and it shows that when we make the frequency higher, our method has the stronger strength in such case compared with the other results. Furthermore, our method is robust to the change of the distribution of the drying path. So in this test, in the testing data set, we use a fractional Brownian motion with a Hertz parameters 0.4, and our result, the finding is consistent with that I showed you before. So I think that's all I want to present today.
Any questions? Prof?
The bringing of the differential equation in the third or fourth slides, like the dy t is equal to d of xt, is it because to capture the temporal information, the change in y and the change in x? The signature basically. Is that the signature, or that's just bringing the temporal information? Because one is the effect of x over y, and another is effect of x1 and x2, like the temporal information and the mapping signature.
So control differential equation is a model which can capture the temporal information, and the change in y depends on the yt and also depends on the change in x. But I mean, control differential equation is actually very general model for the control systems. But of course, I think the rough path theory originally is used to make sense of the control differential equation driven by very rough signals. We study this case because we want to have some theoretical understanding about the error estimates. Because if we have such underlying models, we are may able to get some error estimates of the algorithms.
Another quick thing is, like when you said the end, if we increase the sampling frequency, it's gonna get a higher performance as well.
Yeah.
So does that lead to, like, if we don't sample at all in the first place, use all the cases, it's gonna get even better, right?
Yes. So if the signature is not obtained by computing those iterating integrals out of the discretized path, it's mirrored directly. We expect that the performance may be even better.
Any other questions? No, let's thank Hal again.